Hi again, welcome back. Recall that our goal in these recorded lectures is to prove the theorem that's on the screen right now, that if you have smooth, closed, simply connected oriented four manifolds, isometric intersection form implies homeomorphic. There's, again, two parts to this theorem, first part due to Wall and second part due to Friedman. The goal of this video is to prove Wall's theorem. The motto for both parts of this proof, though, both the Wall portion and the Friedman portion, is to what extent can we apply these handle manipulation techniques of scale that we saw in the previous video, to what extent can we apply them to four manifolds? So 5-dimensional cobordisms between four manifolds. Okay. But today we're going to prove Wall's theorem on H cobordisms. So that's that portion that says that with those hypotheses, isometric intersection form implies H cobordism between the four manifolds. So let's get started. If you have isometric intersection forms, in particular, that means the signature of this connected sum four manifold is 0. That's a nice exercise you can think about. It comes from the fact that intersection form behaves very nicely with respect to connected sum. And that is a result of Rocklin and Tom, that then my smooth manifolds M and N are cobordant via some smooth compact oriented 5-manifold W. This has to do with the computation of the 4-dimensional oriented cobordism group. Okay. Precise references will be in the typed lecture notes, so please feel free to go there for that. So now we're in this condition that we're kind of familiar with now, that there's this cobordism between M and N. Right now, this is not at all close to an H cobordism, so we're going to sort of build up to making it into an H cobordism. It's going to be a bit of an iteration, just like last time. We're going to need one, at least, smooth new input. First step into making this cobordism into an H cobordism is to make sure that the fundamental groups match up. So right now, these manifolds M and N at the top and the bottom are simply connected. So I want to make sure that W is also simply connected. This is not that bad. So here's how we're going to do it. We look at the fundamental group of W. W is some compact manifold, so it's normally generated by some finite collection of loops. And then because the dimension is at least 5, I know that these are represented by embedded simple closed curves inside of the 5-manifold. So for each of these embedded normal generators of the fundamental group, I'm going to do surgery. And what surgery means is I'm going to take a little neighborhood of each alpha I. So that looks like an alpha I cross D4. So I'm going to remove that from my manifold W, and I'm going to glue in a D2 cross S3. So you should check that these two manifolds have the same boundary. This thing has boundary S1 cross S3, but so does this guy. So I'm able to remove one and glue in the other. And then I should do so I should do this to ensure that this D2 is the boundary of this alpha I. So in particular, that generator of fundamental group gets killed because it now bounds this disk D2. So by doing this process for each of these curves alpha I, I'm going to get a simply connected cobordism between M and N. So I'm one step closer to this being an H cobordism. And then now this is where all of our warm-up from the previous video is going to really come in handy. Once I have this simply connected cobordism, it's also smooth, so I get a relative handle decomposition. And then, like we saw last time, I can assume that these handles are attached in increasing order of index. In this case, they go from 0 to 5 index handles. And then the next thing we did last time is we said that we can assume that there are no 0 handles, so I can get rid of those, but then I can also take the handle decomposition and turn it upside down. The 5 handles will become the 0 handles, and I can assume that those aren't there either. So by that process, I can assume that my cobordism just has 1, 2, and 3, and 4 index handles. All right, so that's nice. And then one more step. So I don't have an H cobordism yet, but I do have a simply connected cobordism. And then the process of handle treating that I had last time still applies. So handle trading showed us how to get rid of all the 1 handles at the price of getting in some extra 3 handles. So I can make sure I can get rid of all of these by adding some more 3 handles. And then once again, I can turn the handle decomposition upside down. And then the 4 handles will become the 1 handles, but I can get rid of all the 4 handles at the expense of adding in new 2 handles. Okay, so at the end of the handle trading process from the previous video, I can make sure that Microbordism looks like this. It has this super nice piece, as always, n cross interval, and then 2 handles, and then 3 handles. So Microbordism now looks like it is very nice and simple form. Okay. So now we have to study this handle decomposition a little bit more closely. So here it is again on the left-hand side. And this middle level, after all the 2 handles have been attached, I'll call that M1 half. And then the question that we need to understand is what is M1 half? So we know M1 half is obtained by starting from N4 cross interval, and then so N cross interval and attaching 2 handles, but I know that N is simply connected. So that means that there aren't many interesting simple closed curves inside of simply connected 4-dimensional manifold. In particular, what I know is that each of them is trivial. Each of them is the boundary of a disk, in fact, an embedded disk from the exercise last time. And so all these 2 handles that are being attached to go from N to M1 half, they're all being attached along trivial circles. So here's what this looks like. So here's N1 half, N cross 1. That's where all the 2 handles are being attached. And then here's a 2 handle that's being attached. It's being attached along some curve alpha. And what I know is that that alpha is the boundary of some embedded disk, delta 2. And so that delta 2 is the thing that shows up right there. And so I have to understand what is the effect of attaching this 2 handle to N cross 1 half. So remember, I've just drawn the core here, but really the 2 handle is thickened. That's that cross D3 factor that I haven't depicted in the picture. So what I notice is that I start with N cross 1, and I have to remove the attaching portion of the boundary from N cross 1. So that's alpha cross D3. That's removed from N cross 1. And then I have to add in the rest of the boundary of that 2 handle. That's a D2 cross S2. So basically, this D2 cross D3 has 2 portions of the boundary. There's a portion of the boundary that we use to attach. That has to be removed from N cross 1. And then there's the rest of the boundary that looks like this, that gets added in. So in fact, if there were a single 2 handle in this cobordism, then this would be precisely M1 half. And then in the case that there are more handles, I have to do this process as many times as there are 2 handles. So if we look at this a bit more closely, we see that the effect on N is precisely connected sum with one of these 2 options. You either get an S2 cross S2 connected summand or an S2 twiddle cross S2. That's the twisted S2 bundle over S2. Andras mentioned that in his lecture. So let's try to convince you of where these bundles come in. So this S2, the second factor in each of these cases, that's precisely that S2. So in this handle attachment picture, there's that belt sphere that shows up when I attach the handle, and that's precisely that S2, that second factor. And then you might be wondering, what about these red guys? Well, the red one, that's quite interesting. I'm going to take this D2, this core D2, and then that core D2 union the delta 2 that I have in my picture, that's precisely an S2. So this union of that embedded disk bounded by the handle attaching circle in N cross 1 and the core of the handle coming in, that's precisely the first factor of these summads. And then then it's kind of easy to see that there are these two options. You can either have the trivial product or you can have this twisted product. And the reason, and the question is like the framing by which this two handle is being attached. And you should think about this some more. It turns out there are precisely two framing options, and one of them will give you the trivial product, and then one of them will give you the twisted product. That's sort of the generic case. Okay, it turns out that we can actually assume that you only get these S2 cross S2 summands. So I'm going to sort of skate over this a little bit just because this is not super relevant moving forward. So let me sort of leave it for you as an exercise. One aspect is that if you have a non-spin, closed, smooth, simply connected four manifold, then if you do connected sum with the twisted bundle, that's the same as doing the connected sum with the untwisted bundle. So in that case, if M and N are non-spin, then it kind of doesn't matter which framing you had here. It's always diffeomorphic to just assuming you only got S2 cross S2s. And in the spin case, you should really have started off with a spin bordism between M and N, in which case everything also works out. So I'm going to assume moving forward that this M1/2, this middle dimensional piece, this is obtained from N by connected summing some number of S2 cross S2s. Okay. All right. So continuing on, here's what I knew about Microbordism. I knew that it was built from N cross interval by attaching two handles and then three handles. But here's something I could do. I'm going to just cut along M1/2. So now Microbordism has been split into two pieces. And then this top portion, which contained three handles, I'm going to turn that upside down. And so upside down, three handles, because I'm working in dimension 5, those are two handles. So now I have these two pieces. This first piece comes from N cross interval by adding two handles, and the second piece comes from M cross interval by adding two handles. And so the argument from the previous slide should tell you that this middle piece, I can depict that in two different ways. It's either the connected sum of M with some number of S2 cross S2s, or it's the connected sum of N with some number of S2 cross S2s. All right, so right now this is not necessarily an H-cobordism, this thing I had on the left, but remember my plan is to somehow improve this to an H-cobordism. Here's a result of Wall that comes to our rescue. I'm not going to prove this, but it's a nice theorem. This theorem says that if you have a smooth, simply connected four manifold with indefinite intersection form, Andras defined those in his lectures, then automorphisms of the intersection form of this connected sum, these automorphisms can be realized by diffeomorphisms of these connected sums. Okay. And so this is quite nice. This is telling us something about how I can realize interesting gluings of these two pieces. So initially they were glued together by some identity map. That's great, that's what gave me the original H-cobordism. But what I can do is I can choose to reglue these two pieces using some interesting diffeomorphism of these two sides. And I want to do this so that the resulting thing is now an H-cobordism. So this is my plan. I'm going to take the same two pieces as above, and then I'm going to reglue it using some interesting diffeomorphism of these two pieces. And how am I going to do this? I'm going to do this precisely so that this homology condition is met, so that the result of regluing no longer has any homology. And then because this thing is simply connected, and I have a cobordism which is simply connected between simply connected four manifolds, we saw earlier that this homology condition is precisely a characterization of when that's an H-cobordism. So we have to think a little bit about what precisely is this phi. This is not too bad. Again, I'll write down some details in the lecture notes, but basically the point is that we need the attaching spheres of the three handles to algebraically cancel out the belt spheres of the two handles. And that tells us what we want on the algebraic level. And then this theorem of Wall tells us that this thing that we have on the algebraic level, they can be realized by a diffeomorphism on the topological level, on the smooth level. And then lastly, in case you're wondering about what about this extra connected sum factor of S2 cross S2, that turns out not to be a big deal because we can always add in either we already have an extra S2 cross S2, or if we don't, we can always add a canceling 2-3 handle pair to make sure that there's an extra S2 cross S2, depending on whether N and M have indefinite intersection form or not. But the moral of the story is that we came with this cobordism. I can split it into 2 halves, and then I attach those 2 halves together by a different choice of diffeomorphism that's given to me by this theorem of Wall. And by ensuring that the homology is now trivial in this reglued portion, I get my H cobordism between the 4 manifolds that I wanted to begin with. Okay, so that is the proof of Wall's theorem on H cobordisms. And what we've shown so far is that smooth, closed, simply connected oriented 4 manifolds with isometric intersection forms are H cobordant. Okay. Before continuing a little bit longer, I wanted to give you a quick side note on the Quark theorem, just because this is kind of related to the techniques we've talked about so far. The Quark theorem is a theorem of Curtis, Friedman, Xiang, Stong, Bijaka, and Matveyev. The first 4 in a joint paper, and then the others separately. Again, precise references in the notes. This says that if you have closed, simply connected, oriented, smooth, H cobordant 4 manifolds, then that H cobordism can be split into 2 portions. There's a middle portion, A, that's a sub H cobordism with pieces A0 and A1 in M0 and M1. And we can do the splitting so that away from that sub H cobordism, you have a product. Okay. And then moreover, the portions where the sub cobordism intersects M0 and M1, those portions are diffeomorphic to each other, and they're also contractible. So here's something that this theorem proves for us. Wall told us that if you have manifolds with isometric intersection forms, smooth, closed, simply connected, oriented, whatever, then there exists an H cobordism between them. And then this Quark theorem is telling you that there's a sub H cobordism in which all of the interesting stuff is happening. And so what this theorem is telling us is that, well, what's the difference between M0 and M1? So M0 and M1 are related by, I can take M0, remove A0, and add in A1, and that's precisely M1. And A0 and A1 are diffeomorphic. So I can go from M0 to M1 by removing a contractible piece and then regluing it back in some interesting way. And so that's precisely the Quark theorem that tells you that simply connected, closed, oriented 4 manifolds with isometric intersection forms, they're related precisely by a Quark twist. And then if you now add in Friedman's result, that's telling you that exotic, closed, simply connected, smooth 4 manifolds are related precisely by a Quark twist. Lisa will tell us more about quarks, but this is sort of to tell you that the techniques into proving this result are very similar to what we've seen today. Here's a quick sketch of the proof. We start once again with an H cobordism, just like we did in these last 2 proofs that we've talked about. We can assume that the H cobordism just has 2 handles and 3 handles. And then this middle level M1 half, that's precisely the stabilization of M0 and M1 with some number of S2 cross S2 summands. As before, we can assume that there's only S2 cross S2 summands. It's not a problem. And then how do we build this A? How will A live inside of here? We make A contain all of the handles of W. So W has just some finite number of handles. So if I make sure that A contains all of those handles, then the complement of it will of course be a product because it doesn't have any handles. And that's precisely what it means to be a product. There are no handles. And then what we have to do this extra step to ensure that A is contractible and then its two sides are diffeomorphic. So that requires a bit of care, but you can sort of do it by examining what this middle level looks like and how things interact in there. All right, so that is a very sketchy proof, but at this point, we more or less know most of the techniques that go into this proof. Okay. And then finally, returning to our goal, next time, we're going to focus in on the second part of the proof of this goal theorem. We're going to look at the Whitney trick in dimension 4. I'm going to talk about the disk embedding theorem. And then finally, we're going to prove that theorem that if you have smooth, closed, simply connected, H-cobordant oriented 4 manifolds, then they are in fact homeomorphic. So that's coming your way in the next set of lectures. See you then.